So where we left off last time, we were essentially talking about per phase analysis. So what we saw was that, right, we know that, especially in transmission systems, less so in distribution systems, we're going to be dealing with a three-phase representation, right? Calculating or solving that system in a three-phase form is going to be more difficult, okay, than a single-phase system would be. And that's just obvious, right? You have three of everything. However, there's a shortcut. If we can assume that the system's balanced, we can use what's called per-phase analysis, right? Which means that if all the voltage sources, all the transmission lines, all the loads, if they all have the same values and the same structure, then we'll just forget about phases 2 and 3, or phases B and C, and we'll solve phase A, and then we'll just copy the values over with the appropriate shift. What's the shift? Let's say you have a voltage waveform. What's the shift?
120 degrees.
120 degrees, right? Negative, assuming a positive sequence. Remember we talked about positive sequence and negative sequence? A, B, C versus A, C, B. It'll either be negative 120 degrees, positive 120 degrees compared to phase A, or the opposite. Now, how does per phase analysis loop back into our discussion of Y and delta connected loads? So, well, why don't I ask you? How does that tie?
Can you repeat the question, please?
How does the use of per phase analysis tie into our use of Y and delta connected loads, which one we prefer? Right, we talked about converting back and forth, although I haven't given you the specific equations yet. In a per phase analysis, which would you rather see? Yeah.
Why?
Why? Okay, and the reason for that is because we're in a single phase or per phase analysis, our circuit is going to be representing the voltage between A and neutral. B and neutral and C and neutral are not going to be in the diagram, okay? So the delta connected load or the delta connected generator is not, we can't use it in that form. We're going to have to always convert everything to a Y connected form and then use that in our circuit.
Dr. Deese? So if you have a Y connected load or a delta connected load,
Sure.
So like if you're plugging something into the wall, A, B, and C are the holes, and then the load I mean, how's it sort of set up, if you know what I mean?
Well, I mean, the simplest answer is that your socket in the wall, right, that's just a single phase anyway. You have only one phase running.
Okay.
The three phases come in, let's say come into TCNJ, and then they get split up, but you know, a single phase may only run to a certain building, or two phases may only run to a certain building, and most definitely a single socket is only one phase.
Okay. All right.
So when we balance the system out, what we're trying to do is say, okay, 5 classrooms will be on phase A, 5 classrooms will be on phase B.
I see.
Aren't some like I think like sockets and like let's like a washer and dryer.
Yeah,
they
there's the
also-
30 amp plugs. So a 30 amp plug would be two phase, and you know, I never thought about that. That must be delta connected to get the maximum voltage between the.
So the power comes in at TCNJ, and then those, like, if we have 3 different buildings, those would be the different resistances, those loads?
It really depends on the structure. First off, there's probably something in this building that requires three-phase power. A large HVAC unit for a building like this probably requires three-phase power. And so in that case, it would be connected as such. I don't know if it's a delta or Y connected configuration. But anyway, that's not a regular, you don't plug that into the wall, right? That's something that, you know, a technician would come out and hook it up. So, yeah, I mean, even in a residential home, like you said, they all have 30 amp sockets, so you have at least two phases going in.
Okay, I see. All right.
Okay. So, and we're going to be discussing this more from a textbook fashion or textbook point of view anyway. We're not gonna get into as much of the you know, what are two-phase loads versus what are three-phase loads. We're really just gonna be talking about like big, medium, small. We know that anything that plugs into a socket in the wall is gonna be single phase. We know large machinery is gonna be three-phase, and then, you know, two-phase will fall somewhere in the middle. But a lot of times, I mean, like most textbook problems, it'll be represented by a constant power draw, or it'll be given an impedance, and we won't be going into too much of it. Okay. So, now the last thing that we talked about last time was coupling between phases. So, there's a couple of assumptions that we need to adhere to in order to use per phase analysis. One of them is that it has to be balanced, the system, right? Another one is that we don't necessarily have to ignore the mutual inductance between, or the mutual impedance between different phases, but we do have to find an appropriate way to represent. So what is the coupling between phases? It's the mutual impedance between, right, those lines, which in most cases is going to be represented by an inductive element, right, which represents the magnetic field generated by the individual lines running along the transmission grid. There's also coupling between the phases in synchronous machines, right, because those also have a magnetic component to them, but again, we'll find a way to represent that as an equivalent within the machine model. Okay, so we don't have to ignore the mutual inductances, but we do have to find a way to represent them accordingly. So, in a balanced system, we can ... So what can we do? Hopefully this pencil's charged enough. So the first question we're asking ourselves is, how can we represent mutual inductance in a balanced three-phase balanced system?
We don't worry about capacitance.
Well, actually, I'm using the word inductance. Really, we're going to be representing it as an impedance. So our calculations would take into account, you know, even if there was a mutual resistive element between the phases. But right, just for the sake of conversation, we're most times going to call it mutual inductance, because that's the primary component. Okay, so one way that we can handle the mutual inductance or the mutual impedance is proper spacing of the transmission lines. So I'm not going to draw that on in the notes, or at least not go into too much detail, but there's something we call transposition of the lines. So if you think about three lines like this, okay, A, B, C, the mutual inductance experienced by B, let's say B is the middle one, is going to be more than the mutual inductance experienced by C or A because of the spacing of those lines. So there's two different ways that we can address that. One would be to use a spacing like this, right, where we, as opposed to putting them flat on the horizontal plane, we can space them like this so that the mutual inductance will be the same for all three of the phases with respect to one another. That's not so much used in the United States. You see it more in Europe. It was used in the Soviet Union. But another way that you can deal with it is what's called transposition of the phases. So what if we do this? We go, oh my God, it's a little bit hard to draw. draw the arrow there. Essentially, every section here, right, you see what we're doing is we're moving the transmission lines so they go top, middle, bottom, then it goes middle, bottom, top, boom, boom, boom. So by transposing the lines and switching their position over a distance, and the average mutual inductance they experience should be equal, right? So that's another way that we can account for that. So I'm not gonna spend too much time drawing those nicely. I'm just gonna put here, we assume that transposition is used. Okay. Now, that doesn't, however, represent the mutual inductances. That's just a way of ensuring that the mutual inductances are balanced on all three phases. We still need to represent it. So, let's draw a picture here for a chunk along a transmission line. So we have okay, and this right here is the total impedance between nodes A and capital A. Now, what is that going to be equal to? It's going to have two different components. It's going to have what we call its self-inductance, as well as a mutual inductance. You may ask, why do I use minus? It just has to do with the sign convention that we're using. It could also be represented as a plus. But in the end, well, the main point is that the total impedance along this chunk of the line is equal to a self-component, self-impedance, as well as a mutual impedance, with the other two phases which are not shown in this picture. Okay, so now, how do we define ZAA? Okay, that value here. How do we define it in more detail, actually, is what I should say. So we know that our voltage, VAA, is going to be equal to a function of three different currents, IA, IB, and IC. Okay? Right? Because all three of the phases will have an effect on VAA. So now, how do we break that out into the actual expression? The first one's easy. We know that the coefficient of IA will be what?
1.
Nope. Let me draw it here. Z. But so ZAA we broke down into two other components.
Z little a.
Well, no, the two components we broke it down to were Z self and Z mutual.
That's Z self.
Z self, right? Okay, because then what we're gonna have is IB. That's gonna be multiplied by what? So it's gonna be multiplied by, if you can imagine ZA, right, is kind of emanating out to the other phases, right? Because it also includes the mutual inductance. So IB times the mutual impedance, which again at this, for this expression, we are assuming there is only one mutual value because transposition is used and therefore ZAB is equal to ZAC is equal to et cetera, right? So all the mutual inductances are equal to one another. So we don't have to represent them by their individual. We don't have to represent what two phases are involved. We can just call it mutual inductance or mutual impedance. And then lastly, we'll have IC, which will also be multiplied by the mutual value. Okay, now,
Professor,
yep,
the mutual impedance was subtracted above. Why is it summed for the?
so we'll talk about that in a sec. First off, these two expressions here aren't related yet, okay? We're going to relate the two together in a second. All we've been doing so far is just pulling out the self and the mutual values. The equation that's in the green, using the minus there, all that does is define what our ZAA value is. Okay, it's just, again, we made up that value, so we can use plus, minuses, whatever we want to. We'll see in a second that using the minus there helps with when the final form of this equation that's in the red, you'll see that it makes sense why we use a minus right there. But that minus doesn't really have an implication on this right here as an example.
Professor?
Mhm.
So for lines B and C, you don't take account of the self-impedance when you're
You
calculating?
do when you're calculating VBB and VCC.
But not for VA?
Well, no, because the self-impedance for phase B only has an effect on itself,
Okay.
right? So, yeah, like,
That's just like the impedance of that line, right?
yeah, the self-impedance, the impedance of that line, the impedance that the regular old, like when you work with DC circuits, that would be the self-impedance or self-resistance is just a resistance along the line itself. The mutual is represented by, most times, it's mutual inductance that you're experiencing. So yeah, so the voltage drop associated with the self-impedance is only felt on that line itself. Does that make sense?
Yeah.
The self-impedance is the actual resistance and inductance on that line.
That would be there.
That would be there even if there weren't two other phases. So let's say you run a single line by itself, these two go away, you're obviously going to have an impedance along that line. Okay? Now, when you have an inductor, right, it creates a magnetic field, and let's say 70% of that magnetic field is contained to that actual inductor that's on that line. That's the self-inductance. Okay? a certain percentage of that magnetic field is going to be transmitted, or the power associated with that magnetic field is going to be transmitted to another one of the phases. It's going to reach another one of the phases. That's the mutual inductance that we're talking about. So,
If it's close enough.
if it's close enough. It's really hard, I mean, and also I probably haven't, I don't want to use the wrong language here, because this is not really part of the lecture, but yeah, that's the best way of looking at it. Think about this as the impedance that would be there even if it were by itself, and there were
Okay.
nothing else, and then these two are associated with the coupling between the phases.
Okay,
That kind of cleared up?
yeah.
Okay, good, yes.
Is that why when they use like the big like metal power lines, they space them out like pretty far so that because they're sending so much like current through it that they want to reduce the impedance from the other lines?
That's part of it. I mean, the main part is they use probably the minimal spacing that's required to prevent a flashover. They want to, right, the closer they are, the greater chance you have of actually having an arc, right, a physical spark going between the lines. But, I mean, I'm sure the mutual inductance also. And mutual inductance, we'll see, is not necessarily a bad thing, right? It's just, if we want to properly model the way that the system works, we have to take into account, we can't just ignore it. Okay, so, now going back to what we have here, can we simplify and so that equation is that one. And the answer is, yes, we can. With the knowledge that this holds true. If you remember, that was one of the byproducts of having a balanced system, right? We knew that the current flowing along the neutral, which is IB plus IA plus IB plus IC. Sorry, I just want to see if this is recording. That should sum to 0. Okay, so now we can do some substitutions with that, because we also know that IB can be represented as right? That's just the permutation of what's above. And also, right, so we know that. Now what we can do is we can plug that into the equation, which we've already been using, right? We know that VAA is equal to IA Z self plus, now I'm going to substitute in for IB. And I'm going to say this is equal to minus IA plus IC times Z mutual. Right? And then now I can also say that's equal to minus IA plus IB, again, Z mutual. Where this, if you remember, will be equal to IB, and this is equal to IC.
Professor, you said that's equal, but you wrote it's minus,
It is minus. The minus is here.
so it's one equation.
Say it again?
Oh, I see what you mean. Thank you.
Yeah, the minus is there, I didn't really include it in the bracket, but the minus is there. Okay, now, if we take this a step further, so we simplify more, or really what we're doing is combining terms. Then we end up with V AA is equal to, all right, we end up with, the first term is unaffected. Then we end up with this. 2IA, or actually, I don't want to represent it like that. We end up with IA plus IA plus IB plus IC times Z mutual. Does everyone see why that's the case? Right, we take the IA and the IC from the second term, we take the IA and the IB from the third term, we put those all together inside of the parentheses. And now we know that this is equal to 0. And so the next version of that equation will simply look like this. So IA times Z self minus Z mutual. Right? And so now you can see why we use the minus for the Z mutual in the very beginning. We could have used the plus, but it just would have flipped the value. The coefficient. Right. And so that's how we can represent both the self and the mutual inductance on phase A or any of the phases without referencing the currents on the other phases, right? So, and these two together, like we said before, we'll just represent that as a single value, which we'll call ZAA. And as we move on to later and later problems, you'll see in a lot of cases we don't even differentiate the two. They'll just tell you, they'll either give you the impedance matrix or they'll say the equivalent impedance for phase A is 2 plus J10. And the mutual inductance will be included in there. But you should understand that that value, that J10, represents both the self and the mutual inductance. Or impedance. It is. 99% of the time it's okay. So now, section 2.4.3. is line-to-line voltages. So, so far, we have been dealing only with voltages that look like VAN, right? VBN. That's called a phase voltage or a line to neutral voltage, okay? The line-to-line voltages are like what you would associate if you were trying to measure the voltage across one of the components in a delta device. A to B, A to B, B to C, BC to A. So the actual description of what a line-to-line voltage, I mean, conceptually it's easy to understand. What we're going to get into in this part is what are the equations that we need to go back and forth. Because if you do a per phase analysis, you're going to end up with all line to neutral voltages. And then the problem may ask you, what is the voltage across you know, the AB component, and then you're going to convert that to a multiple. Okay, so, so how are they related to one another? If we draw a picture here, we can see, right, we have our, this represents our neutral, our phase A, our phase B, our phase C. And so this would be not exactly even, but this would be our, so this is A, this is B, this is C. This would be our VAN plus minus. This would be, that's N. This would be your VBN plus minus. Your VCN plus minus. Okay. Then you have the voltage between those two phases. That would be your VAB plus minus. Your VBC plus is on this side, minus is on this side. Anyway, you get the gist. VCA, vice versa, et cetera, et cetera. Okay, so equation 230 from the book lays out the most basic description, which, as you would expect, VAB is equal to VAN minus VBN, right? VBC is equal to VBN minus VCN, and VCA is equal to VCN minus VA. I'm going to try to write my V's so they look less confused. That's just a habit. Okay, so that is the most basic representation, but it's not going to be super useful if we're trying to do the type of conversions we need to go from a per phase to from a three phase to a per phase analysis. So is there another way of looking at this? Okay, so if we take a look at our voltages as phasors, which is going to be a similar looking diagram, but a little bit different. So let's assume that our VAN has an angle of 0 degrees. So that's our VAN. Our VBN is going to have the same length, right, but it's going to be shifted by 120 degrees, so that should be 120 degrees in there. And then our VCN looks like that. Okay, so now let's try to draw VAB. So that's equal to, like we said before, VA minus VB. So the next thing, or VAN minus VB. So the next step in doing this is we need to figure out what is the vector minus VBN, right? Because that's the one we're gonna be, it's easier to sum vectors together than it is to subtract. So let's draw VBN, or negative VBN, which is just gonna be VBN flipped by 180 degrees, right? So this over here, this is minus VBN. And now, if we, and I drew this too close in more space. So now, if we combine these two vectors together, we'll get a projection that looks like this. It'll be a longer vector, right? Because we're going to be summing together the length of VAN and VB, negative VBN. And the angle, right, is going to be in between the two. And so this right here is going to be a 30-degree angle. And this right here is our VAB. And so how do we, and I'm going to try to draw this a little bit better. The way we actually do this, right, is we do the end-to-end technique. So we imagine we're connecting the end of the blue vector to the, or the beginning of the blue vector to the end of the red vector, right? And then we draw it like that. So that is VAB. And the angle we are going to end up with is 30 degrees. And so what's going on here is, I'll rewrite this, we connect VAN and negative VBN end to end to create projection of VAB. Okay, so what are the expressions that go along with this? These are the conversions that are going to be most useful to you. So VAB is equal to square root of 3 times the magnitude of VAN shifted by 30 degrees. VBC is going to be equal to shifted by, I have it in radians, so negative pi over 2, what is that? Pi over 2 is that 90? 90 degrees. And then VCA is equal to square root of 3 VAN. Remember that we're only taking the magnitude of VAN. If you wanted to, you could say magnitude of VAN, magnitude of VBN, magnitude of VCN, but they're balanced, so all the lengths are the same. That was, oh yeah, so they're all the lengths are the same. So you could write it. You could write them all in terms of the length of VBN, or all in terms of the length of VCN. They're all. And then I should have just written these in radians because I don't know what number it is. 7 pi over 6. Is that right?
Should it just be all 520 degrees? The 270, the third one?
Yeah. Positive 270.
Or should it be
Yeah,
negative?
that would be the same.
I should have just read the way ahead. I'm not much of doing calculations in the 7. Divided by 6 times 7. Divided by 6.28. 210. 210, not 207. Right, because 30 plus 120 gives us a negative 90. Yeah, okay, and then negative 90 plus another 120. Can't do the simple math. 120.
Yeah, because negative 210 is also 150.
150, which is the same, yeah, plus, okay, good. It's early in the morning. I'm not on my A game in terms of doing calculations on that side. Okay, so, the last thing I'll write here is that each one, so for each phase, the line-to-line voltage is square root of 3 factor longer than the line to neutral. And has a 30-degree offset. With respect to that individual phase, right? If you remember, VBN has an angle of negative 120 degrees, so VBC is negative 90, and VCA would have an angle of positive 120, which is negative 240, and you have the 30-degree offset, which brings it back to negative 210, which again reinforces it. Yes?
Where's the root 3 come from?
Well, I mean, we don't